Oh, welcome to the video. Today we're going to look at section 4.1 where we're going to be graphing polynomial functions. And in this course, start with each lesson has an essential question. Um, through the lessons and stuff like that, we're going to try to answer that essential question. In this case, the essential question for this lesson is, what are some common characteristics of graphs of cubic and quartic polynomial functions? Well, first off, we need to know um, what those kinds of polynomials are. First off, if you look at a cubic function means it's a third degree polynomial. Third degree means that the largest exponent attached to a variable is to the third power, and a quadratic is where you have a fourth degree polynomial. We've spent quite a bit of time with quadratic functions and linear functions and stuff like that, and this is just the next progression in in um, in those graphs. So some of this might be a little bit of a review, but what we want to be able to um, figure out is a specific function a polynomial function? And if it is, we want to be able to rewrite in standard form, state its degree, state its type, and in this case, they want you to use the lead coefficients. So let's look at the first example. So the first example, it says it's f of x is equal to negative 2x to the third plus 5x plus 8. Now, for a function to not be a polynomial function, here are some of the characteristics, and you can kind of make a list of this. So I'm just going to put like not right here, okay, and kind of make this list. So the first thing is variable exponent. So if you notice anything that's raised to the um, x power or y power or something along those ends, it can't be. Another thing that we cannot use is when it comes to exponents is it can't be a fraction exponent. So it can't be raised to like the 1/2 power or 1/3 or 2/3, stuff like that. It can't be a negative exponent. So a lot of things that tie into a function not being a polynomial a lot of it is directed with what the exponents are that are attached to the variable. Okay, so if you look at the first example, there are no variable exponents, there are no fraction exponents, there are no negative exponents, so we can move forward with the problem. Standard form, uh, in the past, same definition applies. It's put the term that's got the largest degree in front and then go in decreasing order from there, where our constant value, our value that doesn't have, our term that doesn't have a variable at the end. So at this point, how it is written, it's the standard form. Stating its degree, it is a third degree polynomial. The type, because it's a third degree, it's cubic. And the lead coefficient is the number that is attached to the term with the largest degree that happens to be -2. Okay? If you look at example B, that is, in fact, a polynomial function, has all the characteristics. There's no negative exponent, there's no fractional exponent, there's no variable exponent. We can go from there. It is not written in standard form because my largest degree is to the fourth power. And so we got, to rewrite this, is going to be g of x is equal to the square root of 2x to the fourth minus 0.x to the third minus 12. The degree in this case is a fourth degree. The type is the quartic. I have a hard time saying that. And finally, the lead coefficient in this case is the square root of 2. Now, if you look at C, this particular one has a negative exponent, -1. So this one is not a polynomial. So it makes it pretty simple. And I'll do D real quick. It's written in standard form. It's a second degree. It is a quadratic because it's a second degree. And the lead coefficient in this case is 1. All right. So here they have some other examples of basically what we just did. I encourage you to take a look at these, give them a try. If you have any questions, please comment down below. And I'm more than happy to entertain any questions that you may have. The next thing that they're asking us here is they want us to evaluate a function. So they have this function here, f of x equals 2x to the fourth minus 8x squared plus 5x minus 7. And we're evaluating it when x equals 3. Now there are two different ways that we can solve this. Both ways you're going to get the same result. So the first one is direct substitution. This is probably the method you're most familiar with, where you just substitute 3 in for x and then use order of operation to help you solve it. So from there, we got 2 times 3 to the fourth power minus 8 times 3 to the second power plus 5 times 3 minus 7. So order of operations says we got to take care of the exponent. So 3 to the fourth power is what, 81. So it's going to be 2 times 81 minus 8 times 9, because 3 squared is 9, and then I'm going to go plus 5 times 3 minus 7. So now we'll take care of all the multiplication. So 2 times 81 is 162 minus 8 times 9, which is 72, plus 5 times 3, which is 15, minus 7. Take, do all of the addition and subtraction now. We get a result of 98. So when we evaluate this function when x is 3, our result is 98. The other method that you may not be as familiar with, but you're going to get quite a bit familiar with it throughout the course of this chapter, and it is called synthetic division. So synthetic division simply means this. So we take the value that they want us to evaluate, and I'm going to write down here is a 3, and then you kind of make like a half a rectangle. And on the top here, you're going to fill in the coefficients of the function. Now, what makes this one a little bit tricky is if you are missing any terms in the function, you must replace it as a 0 coefficient. So, for instance, this function here would actually be written as 2x to the fourth, and since there's no x to the third, it's going to be plus 0x to the third minus 8x squared plus 5x minus 7. You know, to the fourth power, to the third power, to the second power, to the first power, to the constant. We have all of it there, so we can go about and solving it. So now all you're going to do is you're just going to look at all of the coefficients, all right, and make sure that if it's positive, it's positive, if it's negative, make it negative. So I'm going to write positive 2, 0, negative 8, 5, and negative 7. And at the end of this, you're going to get the same answer as we did when we did direct substitution. So what you're going to do is you're going to drop down the 2's, you're going to write in a 2. Then you're going to multiply 2 times 3, which then you get you 6. Add 0 to 6 together, to get you 6. Multiply now 6 times 3, which is 18. Add negative 8 and 18, which gets you 10. Multiply 10 times 3 now, which gets you 30. 5 plus 30 is 35. 35 times 3 is 105, and negative 7 plus 105 is 98. We get the same answer as we did with direct substitution. Again, at this point, do what you feel comfortable with, but knowing that eventually that synthetic division will be something that we'll look at quite a bit in this chapter. All right, so now when it comes to graphing polynomial functions, one of the things that we're going to look at, or we're going to have to answer, is the end behavior of a polynomial function. Now, when it comes to the end behavior of a polynomial function, you're really only interested in two things in the function. First, is your lead degree odd or even, or is your lead coefficient positive or negative? So if you look at the chart here, in these first two graphs, both of these graphs have an odd degree. So to the first power, to the third power, to the fifth power, to the seventh power. Those are all odd degrees. If you look at the graph on our left, this one right here, this one is a representation of a polynomial function where your lead coefficient is positive. So if you look, where does your graph start? So anytime you're looking like where does the graph start, imagine it like you're trying to read a book, you're going to go from left to right. So your graph starts here, kind of at the bottom of the graph, all right? It finishes at the top over here. So what they are asking you to do is figure out, okay, X, if you pick X going this way, you are going to just keep going on and on forever into infinity. So when X is a really large negative number, so like as X is going to negative infinity, f of X or Y is going downward as well. It's going to negative infinity. That's what this statement right here is telling us. Coincide as X is getting larger and larger in a positive sense, f of x is also getting larger and larger. That's why it's rising. So f of x or y is going to positive infinity. Looking at the graph on the right, this is a situation where we have a negative lead coefficient. So when we, again, now where does our graph start? Well, our graph starts here up at the top and then it ends at the bottom. So it's from going from left to right, it goes from the top to the bottom. So that means when f of x is at positive infinity as x is getting smaller in a negative, or larger in a negative sense, and then as it finishes, as x is getting to positive infinity, f of x is going downward to negative infinity. So that's what happens when a function has an odd lead degree and is either positive or negative. If it is even, all you have to kind of look at, really is what is our lead coefficient. So when our lead coefficient is positive, if you notice, it doesn't matter when it starts or when it finishes, it's going upward. So as x is approaching negative infinity or as x is approaching positive infinity, it doesn't matter. F of x is going to positive infinity in both directions. Same thing goes here. As it starts and as it finishes, when our lead coefficient is negative, f of x is going to negative infinity. So I would say make sure you reference this chart as we move forward so you have a kind of an idea of what we're supposed to look at when it comes to end behavior. So coming here, they want you to describe the end behavior. So first thing you got to do, and all you really have to do, is find the lead degree and your lead coefficient. So it is right here. So your degree in this case is 4, so it's even. And your lead coefficient is a negative 0.5. So we have a degree that is even, lead coefficient that is negative. So the end behavior is simply going to be as f of x will approach negative infinity as x approaches negative infinity, and f of x will approach negative infinity as x approaches positive infinity. And that's where it'll be on. That'll be on the chart there, and you can reference that certainly as we practice these types of problems. So here they want you to evaluate a function given the terms of x. Um, let's look at let's look at 4. So again, I won't do all of the values, but I will. I'll do some. But again, I encourage you to work on these problems as well. So this one here is going to be, and we'll do direct substitution. So this is going to be negative. So since it's negative x, I'm just going to say it's negative 1 times it by, and it's going to be 4 to the third power plus 3 times it by 4 to the second power, and then we'll add 9 from there. So 4 to the third power is 64, but negative 1 is going to be negative 64 plus 4 squared is 16 times it by 3 is 48, and we'll add 9. So negative 64 plus 48 plus 9 is negative 7. But let's see if what it looks like using synthetic division. So I got 4 here. So my coefficients are -1, 3, 0 because there's no x to the first, and then 9. So let's see if we get -7. So this is -1, and then this will be -4. So this is -1. And then we got -4 again. So now I got -4. Now I have -16, and I get -7. Same as I got here. Okay. Looking at number 6, they want us to describe the end behavior. So again, let's look at it. Our degree is odd because it's to the third power, and our lead coefficient is positive. So what we essentially you're going to say is f of x is going to approach negative infinity as x approaches negative infinity. And then you're going to say f of x approaches positive infinity as x approaches positive infinity. And that's the end behavior for that. So here, they want us to graph the the function. So what I would do is make sure have your graphing calculator, and let's punch it in. So if I typed in negative x to the third plus x to the second plus 3x minus 3. All right. Before I hit graph, let's see if I can make it look like what this graph will actually appear. So my constant value right here is -3. So I know that it is going to cross the y-axis at -3. Now what I want to do is I'm going to take into account the end behavior. So my lead degree is odd. My lead coefficient is negative. That means if I go back to my notes, that means it's going to start up here because when x is negative infinity, f of x is positive infinity, and it's going to end somewhere down here. It is a third degree polynomial, so it means it has it'll hit the x-axis at least 3 points. And how you can do that is you can kind of make a table. And so for right now, let's do this. Let's get rid of this graph for right now. And if you made a table of x and y, and I just made a series of values. So let's say if I went like -2, -1, 0, 1, and 2. Well, the one with x is 0 will be -3. I believe. I just know that. So if I put -2 in there, it will look something like, let's see here. I'm just going to copy this down so I can see it. All right, so -2. So it'll be what? -1 over -2 to the third plus -2 squared plus 3 times -2 minus 3. So now I get negative 8 here. That means it's going to be positive 8. This is going to be plus 4 minus 6 minus 3. So I get what? 8 plus 4 is 12 minus 6 minus 3. So that's what, 3. So if I put negative 1 in there, so I got negative 1 times it by negative 1 to the third plus negative 1 squared plus 3 times negative 1 minus 3. So negative 1 cubed is negative 1 times, so that's positive 1 plus 1 minus 3 minus 3. So this is going to be what? 1 plus 1 is 2. 2 minus 3 is negative 1. Minus 3 is negative 4. So something like that. Now it will look like as x is 1, so negative 1, and then I got 1 cubed plus 1 squared plus 3 times 1 minus 3. I get 1 cubed is 1, negative 1, so that's negative 1 plus 1 plus 3 minus 3. So I get negative 1 plus 1 is 0, plus 3 is 3, so that gives me 0. So that's one, technically that's one x-intercept. And let's go finally, let's go with 2. So I got negative 1 and then 2 to the third power plus 2 squared plus 3 times 2 minus 3. So 2 cubed is, yeah, 2 cubed is 8. So negative 1 is negative 8 plus 2 cubed is 4 plus 6 minus 3. Negative 8 plus 4 is negative 4 plus 6 is 2 minus 3 is negative 1. So let's plot these points. So negative 2, 3, about there. Negative 1, negative 4, 1, 2, 3, 4. And then 0, negative 3, which I got. 1, 0. And 2, negative 1. So if I know it's going to start here, I'm going to say that my graph is going to look something kind of like this, this, and this. All right, is it perfect? Obviously not, but it just gives you an idea. So let's take a look at, so I typed in the equation here, so let's see what we come up with. Uh, let's go to, let's go turn this off. And then we go to zoom square. Boy, let's try this second. All right, sorry about that. I just had to set up the standard. So when I graph it, it looks something like this. Is it exactly the same? No, but it is close. But it does get you an idea of what you're looking for. So in this case, they want us to find, identify the end behavior, plot some points to go from there, and then at the very least, you should be able to establish what the y-intercept is. And that is being able to graph polynomial functions. Hope this helps. Until next time.